This Week in Science and Education is brought to you in part by the University of Western Ontario, www.uwo.ca. We thank them for their support. This Week in Science and Education is also brought to you by Laurentian University. Check out Laurentian at laurentian.ca. We thank them for their support.
Hey everybody, it's time for This Week in Science and Education. This is your host, Kevin Cougler, broadcasting from the University of Western Ontario. This is T-WiSE, episode 51, Leo and his immune system. Thanks everybody for taking the time to join us today. It's an interesting day here on This Week in Science and Education. We have with us Dr. Lionel Filion from the University of Ottawa, and he's going to talk to us about immune suppression and accessor functions. What are those? Well, we're going to find out right now. But before we do, let's welcome our co-hosts as usual. Let's go with Jagoe, Colin Jagoe. No, that's not you, Thomas. Jagoe from the Kawartha Pinehurst District School Board.
That'd be me. Hey, how are you?
Good, good. How's things in Peterborough?
Oh, super.
Good stuff. Okay, Thomas, now you can wave. Dr. Thomas Merritt from Laurentian University, confusing our guests. Hey, Thomas.
How are you?
Good, good. Very excited to talk to a good friend of mine, Leo, today from the University of Ottawa. Leo, thank you so much for taking the time to join us. It's going to be an interesting chat, and we appreciate your time.
Oh, you're quite welcome. Glad to be here.
So why don't you start off, Leo, by just telling us a little bit about who you are, what your job is at University of Ottawa, and the nature of your research.
My research is, I'm an immunologist. And a lot of people say, what is an immunologist? Well, an immunologist is someone who studies defense. That's all we do is defense. That's just what we do. We want to know how our defense works against viruses, bacteria, anything foreign coming into the body. And this is what I've been doing for the past 31 years since I got my PhD. And it's really cool because it's a beautiful system that has been found from insects all the way to humans. And it's very, very specific. And at the same time, it's not very specific. So it's kind of cool. I study that.
That does sound very
defense.
cool. That was
purely defense.
That was great.
Purely defense. Very simple.
Even I understood
How does the
that.
body defend itself?
So give us a day in the life then, Leo. Are you spending some time teaching? You're spending time in the lab? How does that unfold?
Well, I start my day around between 8 and 8:30, and I do a lot of reading. I have graduate students. I teach at the medical school. I teach in the Faculty of Science. I have a lot of student contact hours, and it's a lot of fun. I write a lot of papers, a lot of grants. I contact with. I have researchers all around the world that I contact, that I work with, trying to understand. I have an Australian project, I have a Florida project, so with leading researchers in their field. So, I finish my day around 5 or 6, and I go home, and I have a wife and some kids, and everything else is all the same.
All right, so I'm going to open up the floor to questions. I'm going to start with Dr. Thomas Merritt. And Thomas, in the spirit of communicating with the University of Ottawa today, please pose your question in French.
Yeah. Give me a second. So, Leo, we got a little blurb. They allow us to do a little bit of homework before these podcasts. And so I was reading through the material that we've sent out. And your lab, according to this anyway, has 3 model systems that you're working on, HIV and MS, and immune suppression. I wonder if you could pick one of those, and any one of the 3 I'm sure would be equally interesting, and just give us a spin on how would somebody bring this into a classroom. If somebody wants to, if a teacher wants to talk about your research in HIV as a model system, what can they take from your research and bring into the classroom and talk to their students about?
Well, the biggest problem with in HIV disease, it's probably one of the most complex diseases out there that we know of. The virus has a tendency to get inside cells and hide. It has a really good ways of hiding inside cells. It kills off a whole bunch of cells called T cells. Okay, they just die. And that wouldn't be so bad because we always form new ones all the time. But there's a cell type that the virus hides in, and it's a macrophage, and it's like a Pac-Man cell, and it just engulfs everything. But what's kind of neat about this particular cell is that once it gets inside, it doesn't kill it. So it becomes a Trojan horse, and it just hides. And then it produces a little bit of virus, and it just keeps on infecting new cells, new T cells, and keeps killing. And the levels of virus keeps going and going and going. And the drugs, they're not very effective against viruses inside these Pac-Man-like cells. They just don't. They don't do well. And it just, it's like the Trojan horse. And then eventually it just comes out and it just overwhelms the immune system, and then you don't do well. A lot of people die from this disease. And these cells of the immune system produce certain factors that are very necessary to promote defense mechanisms throughout the body. And sometimes it produces a lot of certain ones, and then it turns off, it just shuts it completely off, which causes immune suppression. So, which means that you cannot respond to a foreign invader and get rid of it. So it's kind of complex, anyways, go ahead.
Sorry, so, I mean, without even going past that on complexity, you've hit three things that might be really interesting for classrooms and teachers. One, the idea that we haven't been able to combat AIDS with a vaccine, whereas we have with other diseases. And then two is this idea of the drug resistance, and what that means to our treatments. And I've already forgotten what the third one was, so it must have been pretty amazing in itself. But the idea that we can't, or we have yet to be able to come up with an effective vaccine, is that because of hiding in the macrophages, or is that a combination of macrophages and something else?
Well, there's two things. One of them, it does hide in the macrophage. It's also how it gets in. It's really important how it gets in, and it gets in through sexual contacts. You got to think about, in semen, believe it or not, there are immune cells. In semen, your semen and my semen have T cells and have macrophages. So here you could have an infected cell gets introduced into the vagina, and it could get into the circulation of the host. Rejection of something foreign takes at least 3 to 4 days. So even if the virus has time to propagate or change or start dividing and infecting the host cells right off the bat. So, and if it's hiding inside, a vaccine it doesn't really work very well. And even if it was there's free virus and virus inside these Pac-Man cells, the macrophages or T cells, and they are not destroyed by the vaccines that are produced, and these are antibodies. And antibodies react with virus that is free floating. It doesn't react with the virus inside the cell. And then the problem also in the vaccines that we produce is that, are we producing the vaccine that will get to that surface, the vagina or the penis, where the semen is? Can we get the vaccine to work exactly at that particular spot? And that has been a challenge. Prevention is really the key for HIV. Prevention. And if we could make a vaccine that could recognize an infected cell and a cell or free virus, that would be great. A therapeutic vaccine is a vaccine that we would give someone who was already infected for, say, a year or two, and that is a real big challenge, real big challenge. And that one is going to be very difficult. Right now, the vaccines they're putting out, what they're trying to do is necessary therapeutic, but can we have a vaccine that will help the infected individual survive longer with a better quality of life? We would love to see a vaccine that would sterilize the individual from the HIV, get rid of it, but that is many years away. Everybody's striving for that, and there's a lot of money being put into it. The Gates Foundation is one of them, and the federal government, our federal government, and which has a brand new strategy out just recently, and the U.S. government and whatever. But this is a big, big, big challenge.
Dr. Filion, give us an idea of what kind of progress has been made on this over the last 20 or 30 years. You know, I think I remember in the mid-1980s, I was doing science projects in school surrounding this new disease called HIV or AIDS at the time, but I think it had been around for a few years before that and just kind of made its way into the news at that time. What have we done since then, and what kind of strides have we made in that area?
I think the biggest strides is that we could identify how it's transmitted and how to prevent its transmission. That is very, very important. Prevention is really, really, really important. There was a study in Uganda several years ago showing that if you an effective prevention protocol was as effective as a vaccine that was 80% effective. So just prevention really does a big, 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 big issue. So we know that. We know how it gets in. We know where it divides. We have now a combination of drugs that will keep the individuals who are infected, give them a quality of life. But the drugs have huge, huge side effects, and it's not very pleasant for the individual. They have choices, and the choices is either if you're progressing, you're going to be sick from the drug, or you're going to die. I hate to be very blunt about it. So it's not an easy task. So I think those are the major. That's the major findings lately.
Sorry, I think that goes back to the point that you keep driving home, that it's prevention. I know that one of the big deals in one of the major concerns in HIV treatment and just handling HIV in general is in many populations, people have gotten away from prevention because we do have the drug cocktails. We do have ways to treating the disease now, and for the first time in decades, infection rates have started to climb again because people have moved away from really safe practices because, well, you can treat the disease. It's not as frightening as it used to be. And I think one of the points that we need to do a better job of is driving home, oh, no, it's still really frightening. And prevention is the only way to handle it.
Here in Ottawa, there was just recently, the Public Health Agency shown there was an increased rate of infection within Ottawa. And Ottawa is an extremely educated population, and you find that. This is unacceptable. This is really, really unacceptable. And the high schools and whatever have to do it. We have to tell our youth this because it's really, really important. Very, very important. We can't cure this very easily. We can control it, but controlling it gives you still. It's not pleasant to take all these drugs. And having children, eventually, right now, you don't want children in high school. But when you hit 25, from my understanding of most people, they want children. They want a life just like everybody else. Now is not time, but later on, it will be there. And having an HIV infection is not something that you want to carry for 50 years.
Yeah.
And one of my best friends, who's an HIV researcher, tells me, you know how HIV drug works? One of the criteria is that it also fails. So all these cocktails will eventually fail. So we have to worry about it. That's how you know that a drug is actually working. It's actually looking at its failure rate. So the virus keeps changing. It adapts quite easily, and it mutates very, very easily and divides. So the best way to prevent this and get rid of this virus worldwide is prevention.
I'm not sure if Colin is actually with us today. He's strangely quiet, Thomas. I'm not sure what's going on. I think there's just a video of him playing as an overlay. I want to get to Colin in a second, but first I want to tell you a story that talks a little bit about what you're talking about, Dr. Filion, which is prevention. I come from a small town in rural southwestern Ontario, and half the population there is of a certain religious sect. So they don't believe in inoculation or, and so a few years ago what happened was half the town was brought down by a case of rubella. And, you know, that's not as serious as HIV, obviously, but it was half the town was infected almost with this case of rubella that spread like wildfire. And it goes to your point. These diseases are not, they haven't gone away. They are still there, and we still need to be conscious of them. And I think that's probably your one of your messages here today.
As an immunologist, is that yes, the body can protect itself, but it needs common sense attached to it. And the best way to prevention, a lot of people think the immune system is antibodies and T cells. That is not just, that's only a small part of it. The biggest part of it is the prevention of the infection to get in. I spend most of my time in the 2 to 3 hours of at the beginning of my classes showing that the skin is probably the most important organ that we have for prevention. It's part of the immune system. And it's very, very critical. The Nobel Prize given this year has been given to individuals who are not looking at antibodies, but what they call the innate immunity, which is the non-specific immunity that we have. And we're going to have this Dr. Hoffman here at the University of Ottawa on October 21st, and he's going to come. He's going to give a talk, and he's also won the Gardner Prize this year in Canada. So, and he's going to be talking about what they call innate immunity, which is not antibodies or what everybody thinks is the important. The skin is like the oceans, you know. If you want to, if you don't want a country to invade you because you want a best defense system, just put an ocean between the two countries, and they can't come through. And your skin is that ocean. Okay, it is very, very effective at eliminating things. So. We don't want anything foreign in our body. We have to prevent it.
On that note, we're going to take a quick break here for a couple minutes and thank our sponsors, and we'll be right back with Dr. Lionel Filion from the University of Ottawa.
This Week in Science and Education is brought to you by Sheridan Institute of Technology and Advanced Learning. At Sheridan, students shine brighter. Check out sheridanc.on.ca.
Okay, and we're back. Thanks, everybody, for sticking with us on This Week in Science and Education. We're having a fascinating discussion around immunology with Dr. Lionel Filion from the University of Ottawa. And Colin has been, you've been snoozing through the first half? I mean, what's going on over there? Jump in.
I just put a picture up here of myself, and then I went for a coffee. Didn't you see that?
I should have brought me one.
Yeah, sorry about that. It's been very... Yeah, there you go. It's been fascinating just sitting here listening to you guys talk here. And a couple of things have sort of occurred to me as we're talking. When we're talking about how a vaccine works, we're talking about why something like HIV, for example, is really hard to fight. I'm wondering if we can maybe take a step back and get a little primer on the immune system itself. If someone is infected with something for the first time, what actually goes on in the system? Because we're talking about these different bits and pieces not working. Well, how do they work if they're working effectively?
Oh, that's actually part of your curriculum is already teaches part
Absolutely.
of that, which is good.
I think that's why he's asking.
That's sort of why I'm asking, yeah, but thank you.
Remember, I have kids too, so I know what they do.
Perfect.
So something foreign comes into your body. It has to break into the skin. And then within the skin, there's a cell. These are called Langerhans cells. They're a form of Pac-Man cells. They do the same thing. They'll take it up. They'll chew it up. And then they're going to move. They're going to start moving. And they're going to go into the circulation and go to a certain organ called a lymph node. Little lymph nodes. These are all around your body. And most of your students have had their lymph nodes touched. If you have, for instance, influenza, you go to your doctor and you think you got a bad cold. Well, he's going to touch you in your under your jaw. You know what he's measuring? He's looking for lymph nodes. Are they engulfed? Are they larger than normal? And what happens is that these cells go into those lymph nodes, and they start talking to other cell types, B cells and T cells, and they start interacting with one another, and they produce all kinds of factors necessary to make them grow and to make them change into antibody-producing cells. And then the antibody-producing cells start secreting antibodies, and the T cells get activated. And these are T cells are like tanks. Antibodies are like soldiers. And the tanks go out and they'll leave the lymph node and go to the virus-infected cell, and they'll destroy. The soldiers go all around your body very, very quickly, and they'll look for free virus all around, and they'll just gulp them up. And we have specialized Pac-Man cells that will chew up the virus-coded antibodies and destroy them. So you reduce the amount of virus into your system. The tanks go out and they destroy infected tissue. The free virus are mopped up by the soldiers, the antibodies. And what's neat is that the antibodies will last a long, even though they don't last very long, the cells that produce these antibodies, eventually there's a small percentage of them, they become memory cells. Okay? And these memory cells are very long-lived. And in 2008, this is kind of cool. I couldn't believe this myself when I read it. In 2008, people who survived the Spanish flu of 1919, this was published in 2008 in Nature, top journal, one of the top journals in the world, demonstrated that people that were 2 years old and now 90-something years old that survived the Spanish flu had antibodies to the virus of 1919, and they actually had B cells, the cells producing the antibody actually pulled them out of these people. So the memory cell response over something like 90 years.
You know, I got to say, Dr. Filion, tanks, soldiers, oceans, this is the first time I think I've really understood some of the science content on this show. Thank you for that, and I'm sure the students feel the same way. Thomas, save me. Jump in, please.
I'm actually writing notes because I use that Spanish flu example in a course that I teach, where we look at what we know about that reconstructed flu virus. And I didn't know about the memory cell paper, so I'm going to have to look that up to include in
the
class.
Nature August issue in 2008.
All right, that helps. Thank you. That's fantastic. Yet another time I get to use this podcast in class. Excuse me. Okay, so we've talked about this model system and how that can get used in the classroom. You've got a number of other model systems that you work on. Maybe talk a little bit about how you've moved between them. So why is your research group as diverse? What's the commonality between these different factors or the different projects?
Well, if you look at multiple sclerosis, if you look at HIV, I told you it's a Trojan horse, and you're not activating. Multiple sclerosis is exactly the flip side. There's 180 degrees difference being associated, where you get an activation of the immune system that you don't want, and we started looking at that because it was exactly the opposite of the model system that we were interested in, and that told us a lot. Is that we find is that these individuals, even very early in the process of the disease, are immune activated, and normally what you want in most individuals, you want a steady state. You want to be able to activate and turn off at the same time. You just don't want one system to be completely down, the other one completely up. You always want to be right in the middle. In autoimmune diseases like multiple sclerosis, you get an activation. In HIV, you're down. So it's actually 180 degrees. So we started looking at the factors associated with that. And some of the in multiple sclerosis, those are what we looked at were some of the factors that are called cytokines. There's a whole slew, and there's 35 to 37 different products being produced. We started looking at the ones that were being produced, trying to hone on what type of immune response was being generated, and can we turn off that specific immune response? Because the immune response, just like any tank, is to find the status quo. So one is high. So what's been pushing it high, and can we actually turn it off over time? And that's essentially how we look at multiple sclerosis and HIV. It's just the opposite, and it's an exaggeration of the response. But as a scientist in humans, it's very hard to study a disease process when there's a complete steady state. You need to see the extremes, and when you look at the extremes, then you have a way to start measuring things.
Do we have any idea what triggers MS? I mean, HIV, we're looking at a virus that's infected the body, but my understanding is we still don't have a good idea of what's driving MS in the first place.
That is absolutely true. That's true for nearly every autoimmune disease that we know. Yeah. We think, one of the first statements I made, sometimes we know the immune system is very specific, but it's also very non-specific. And to me, what the biggest theory right now is similarity between a virus or a bacteria or an environmental agent that is similar to something in your body. It's called mimicry. It mimics. And the immune system is more like people talk about a lock and key, and that is absolutely true. It's a lock and key. However, the key is more like a skeleton key versus a brand new key. And a skeleton key, if you remember, my grandmother had locks. They were specific for one lock, but you can go to your neighbors and open up her door anyways, because even though it wasn't perfect fit, it was fit enough. Yeah. And that's how we think multiple sclerosis begins. And then with time, the immune response usually gets better. If you could turn on the response, and then that's the response will then keep going over time. Like with that Nature paper, it shows over 90 years, and then it only get better with time. We think that's how most of these autoimmune diseases, including MS, begins. But what is the key that turns on the engine? We don't know.
Is MS on the rise? Yeah.
What we find is that the more northern people, the more northern hemispheres have more disease. Canada has a lot of patients. For instance, in Japan, there's approximately 1,000 patients in all of Japan. There's 60 million people. Whereas I know for a fact that in Ottawa, there's over 1,200 patients just in Ottawa. And it's really geographic. You can really look at the more north you are, the more prone, more disease that we have in multiple sclerosis. So we think there's an environmental factor. We just don't know what it is. Pardon me?
I told my wife we should have moved south.
You should, yeah.
Hey, gentlemen, we're running out of time. Colin, last question goes to you, my friend.
There's so many different things. I mean, I come at this from a sort of a high school science perspective, and there's lots of different ways that we could approach it. As a teacher, what are the key things for students to know about maybe just immunity in general? What would, if you were talking to me as a biology teacher, what would you say that I really should focus on helping my students understand?
Good question.
Oh, that's what is it?
Everything.
I think the most important, everything. I think you got to keep it simple. I think that's the most simple things is that the immune, like even in my class, I give them take-home exams because if I give them the book to read, I don't know the book by heart. I don't know the textbook Janeway by heart. It's 500 pages. When I started teaching immunology, we knew different types of T cells. And there was only, at the time, in 1980, in 84, there was only about 10, we could identify 10 different type of T cells, okay? Mm-hmm. And they were called CD1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I remember up to 20. I used to remember all the 20. And now we're up to over 400 CDs. You think I know them all? Wow. Absolutely not. So the most important thing is that the basic defense mechanisms are present. You don't need to know all the details. There's 35 cytokines that interleukins that I know of, and there were supposed to be 3 more added to the list. People were asking about. Do you think I know what they all do? Absolutely not. Like I told my class yesterday, there's 4 words that you have to remember about cytokines. 4 words, and that's it. Because you can't remember all the details. So in terms of biology, keep it simple. Try to make them understand that it's defense mechanisms and been associated. If they understand that, it goes a long way.
Good. Thank you.
That's what I think.
Dr. Filion, it's been a pleasure talking to you today. I don't want to let you go quite yet because I do have a question from a student that came by email when they found out we were having you on the show. And Isaac is a grade 5 student from Woodstock, Ontario. Isaac would like to know, what is the greatest thing about being an immunologist?
Having fun every day. It's looking at how things work. And it's cool. And it's you got to think about the specificity. We have all the genetic material to recognize. Believe it or not, if you could, I don't know what number, 10 to the 15th or 10 to the 18th. We have genes 10 to the 15th to 10 to the 18th. Genes that produces soldiers to go out there. That turned me on when I was an undergrad. I remember the professor when he brought it up. I remember the lecture. I remember everything about it. So the immune system is cool. It's just, and it's regulated. We don't kill ourselves. How come? I put my heart into you, you reject it. And, but I don't reject me. What's the process? It's really, really a lot of fun. It's just like, it's exploring space. Because this is what you're doing. The immune system is like, to me, I look at the stars and it reminds me of all of the cells that I have. And I know all the stars are different, just like all my cells are different. And I look at the stars and I say, that star head has maybe this, this, and this, and my immune cells have this. And I have to go look at every one of those stars. And this is really what I want to do. And I have a flow cytometer right now. It's a machine that I could actually measure on a cell 20 to 30 different markers at a time on one cell. And it's going to be really cool to do it. It's something that we just purchased at the University of Ottawa. And it's fascinating. And in my lifetime, I'll never know all of it. So if you want to become a scientist in whatever 20 years, it'd be more than, I'm sure somebody will take them. That's
there you
to me
go.
is the most important thing.
Super. Thank you for that answer. Isaac, that answer was just for you, my friend. Thanks for posing the question. Dr. Lionel Filion is an associate professor from the University of Ottawa, an immunologist. Leo, thank you so much for coming on the show today and inspiring those students out there about science. We really appreciate your time.
Thank you very much.
Thanks a lot.
On behalf of Dr. Thomas Merritt and Mr. Colin Jagoe, thanks everybody for tuning in to This Week in Science and Education. This is your host, Kevin Cougler, signing off, and we will look forward to seeing you again, same time next week. If you're a teacher, break time's over. Get back to work. Take care, everybody.